All right, so in today's class, we kind of dove into sketching graphs of polynomials if I gave them to you in factored form. Now, in class, I went through a quick note with regards to, depending on what the exponent of the factor is, that will dictate how the graph looks like at that particular x-intercept. So let's take a look. So the examples that I have here say sketch the following graphs. So let's take a look at the first one. So the first one is y equals to x plus 1 times x minus 3 times x plus 2. Now I want you to notice the exponent for each of those factors. The exponents that exist for each of those factors is just 1, 1, and 1. And based on our discussion in class today, if the exponent of the factor is 1, it's just going to pass through the x-axis just like a line would. All right? So I know that it's going to hit at the following x-intercepts, at x equals to negative 1, x equals to 3, and then x equals to negative 2. Now I'm looking for a sketch, so I'm not looking for a lot of accuracy, but I am looking for the general things like end behavior, making sure that your y-intercept falls in the correct place, making sure your x-intercepts fall in the right place. So let's take a look. So let's say I'm going to do negative 2 here. I'm going to do negative 1 here, and then I'm going to do 3 there. So that's where my x-intercepts, I'm placing them at. And then based on your factored form, you can actually figure out what your y-intercept is going to be by multiplying all the constants together. Not constants, but the numbers of your factors. So in our case here, we're going to multiply positive 1 times negative 3 times positive 2. That's going to end up giving us, in our case here, negative 6. So I know that my graph is going to get a y-intercept of negative 6. So, like I said, now let's relate back to us drawing this graph now. This is a cubic function, right? If I was to expand it, you would get a cubic function. And the leading coefficient of this particular cubic function would be positive, right? Because if you tried to expand it, you would end up getting x cubed. So let's think about the end behaviors for a cubic function. Okay, so a cubic function with a positive leading coefficient. What is the end behaviors? Okay, so the end behaviors for us for this graph would be as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches positive infinity, right? So when I start graphing this, I know what quadrant I should be starting in, right? So as x is approaching negative infinity, y is approaching negative infinity. That implies that I'm starting in quadrant 3 here. So my graph is going to start at quadrant 3. It's going to go through negative 2, just like a line would go through negative 2. So I'm going to start, it's going to go through negative 2. It's going to come down, it's going to go through negative 1, just like a line would. It's going to pass through negative 6, and then it's going to pass through 3, just like a line would. And that's how you produce the graph for this particular cubic function. A sketch, not an accurate graph, but a sketch. So in this sketch, I was able to make sure that my end behaviors were correct, my x-intercepts, and how my graph behaves at my x-intercepts, and then my y-intercept. Now, these ones are, I would say, the easiest because all the factors have an exponent of 1. Let's take a look at something that's a little bit more different now. So let's take a look at this example here. So I've got y equals to negative x plus 2 all squared times x minus 6 times x plus 4. Now take a note of the exponents that we have here. So for x plus 2, the exponent is 2. For x minus 6, the exponent is 1. And then for x plus 4, the exponent is also 1. So we have something a little bit different here. The factor x plus 2 has an exponent 2 there. Remember in class what I said. Having an exponent 2 indicates that on my graph at the x-intercept, it'll look like a turning point, or In short, it will look like a vertex at that particular x-intercept. So let's talk about which x values these are corresponding to. X equals to -2, x equals to 6, and x equals to -4. So let me place these all on my grid. So I've got -2, I've got -4, and then I've got 6 here. And then let's figure out what my end behaviors are going to be. Sorry, not my end behaviors, not yet, that's too fast. We got to look at my y-intercept. Now for this one, it can be a little bit tricky because the +2 here, you got to square it, okay? Because when we expand this, you end up getting 2 times 2 because of the exponent 2 there. So we're going to do 2 times 2 times -6 times 4, and then there's a catch here. We've got a negative in the front there. So that's going to change things a little bit for us. So if we figure out what our y-intercept is here, so we're going to do -1 times 4 times -6 times 4. That's going to give us +96 as my y-intercept. So again, like I said, I'm sketching here. So my scale is a little bit off. So I've got 96 up here. Alrighty. So let us take a look at my end behaviors for this particular function. Now this polynomial here, this is a quartic function. Okay, this is a quartic. And if I take a look at my leading coefficient, if I was to expand this, it actually has a negative leading coefficient. So it's a quartic with a negative leading coefficient. That's going to change your end behaviors. Okay, so a quartic, which is an even degree function, and it has a negative leading coefficient, that indicates to me that as x is approaching -infinity, y is also approaching -infinity. As x is approaching +infinity, y is still approaching -infinity. So what this tells me is that my graph will start in quadrant 3. It'll make its way around the graph, and then it'll end off in quadrant 4. So let's get graphing here. Now, one thing that you have to be careful about is the fact that x plus 2 has an exponent 2 there. That means that at x equals to -2 on my graph, it's going to look like the vertex of a parabola. So let's get graphing. So we've got it starting in quadrant 3. It's going to go through -4 just like a line would, and then it's going to make a turn, and it's going to come down on -2 and bounce back up off of -2. It's going to pass through 96, and then it's going to come down and pass through 6 like that. And that is a sketch of my function y equals to -x plus 2 squared times x minus 6 times x plus 4. So here the difference was that we were looking at this concept here. The fact that at this x-intercept, my graph does a turning point right on the x-intercept. So very much like a parabola's vertex. The last example that I want to take a look at is what happens if one of my factors is raised to the exponent 3. So taking a look at this example, see, I have y equals to -x plus 1 cubed, x minus 2 times x plus 5. So the first thing, we're going to take a look at the exponents of my factors. So I have x plus 1, that's raised to the exponent 3. X minus 2 and x plus 5 are both raised to the exponent 1 here. Now, we're going to talk about the corresponding x values that relate to these factors. So for this one, it's going to be x equals to -1. This one is x equals to 2. This one is x equals to -5. We're going to place those on our grid right now. So I've got -5, I've got -1, and then I've got 2. The next thing we're going to take a look at is our y-intercept. Now be very careful here. There is a negative in the front, which is going to change the sign of my y-intercept. So the first thing that we're going to do is we're going to do 1 cubed times -2 times +5. So positive 1 cubed gives me 1, times -2 gives me -2, times 5 gives me -10. And if I multiply it by the negative that's in the front there, that's going to give me +10. So my y-intercept is going to be +10, which I'm just going to place up there for right now. The next thing we're going to look at is our end behaviors. That's going to show us how my graph is going to look like. So keep in mind that if I was to expand this, this is actually a quintic function. Okay, it's a degree 5 function. And what kind of leading coefficient does this have? This particular quintic function, if you were to expand it, it actually ends up having a negative leading coefficient because of the negative sign that's in front of the polynomial at the beginning. So we have a, not a positive, we have a negative leading coefficient. So think about it. A quintic is an odd degree function, and we now have it with a negative leading coefficient. That's going to change our end behaviors from what we originally know it as. So as x approaches negative infinity, y ends up approaching positive infinity. As x approaches infinity for us here, y ends up approaching negative infinity. So what this tells me is that my graph is going to start in quadrant 2. It's going to make its way through the graph, and then it's going to end up in quadrant 4. Let's take a look at graphing this and putting it all together. So let us start off by what happens when it passes through x equals to -5. Well, the exponent is 1, so that means my graph just simply passes through -5 normally. Then we go on to x equals to -1. Bear in mind, the exponent for the factor x plus 1 is 3. That indicates to me that my graph is going to pass through -1 just like how a cubic function would look like. So I'm going to continue my graph. It's going to make its way back up, and it's going to pass through just like how a cubic function would look like. So it's almost tangent at -1 there. Once it passes through -1, it's going to go up, it's going to pass 10, and then it's going to make its way back down through 2 again, because the exponent for the factor x minus 2 is just 1. And that's it. That's the graph of this particular polynomial. So now that you have an idea of how the exponents of the factors affect how the graph looks, you're now able to make much more educated sketches of polynomials when I give it to you. Now, the only thing that I would be concerned about is making sure that you know about the end behaviors based on what degree the function is and then what the leading coefficient is. So please make sure you practice on your own. We extended our knowledge about graphs of polynomial functions, and we took a look at how the x-intercept or the zeros of a polynomial function might look like if it was to order 1, to order 2, or order 3. So let's take a look at how to create the equation of a polynomial function given its graph. So let's start off first by indicating all of their zeros. So I've got a 0 here, I've got a 0 here, and then I've got a 0 here. So I've got 3 zeros here. And now what we're going to do is we're going to formulate what I call our family of polynomials that share the same characteristics. So I'm going to do y equals to, remember the a, you need the a there because we're going to end up solving for a little bit later on. Now, both x equals to 3 and x equals to 1, those are both to order 1. So it's going to be x minus 1, x minus 3. The tricky one here now comes at x equals to -4. And the reason here is because if you notice the shape of my x-intercept at that particular point, you're going to notice that it looks like a parabola at x equals to -4. Remember what we discussed in class today? When it looks like a parabola, like the vertex of a parabola on the x-axis, that means that for that x-intercept, it is to order 2 for us. So our factor x plus 4 is going to be of order 2, which means to the exponent 2 for us. Now our job is to solve for our a value. So you're going to pick a point from the graph. Now for this one, you might find it a little bit difficult to choose your point. On a test or anything, I will give you a specific point. I will identify to you what point I want you to use. But for our purposes here today, I noticed that I'm going to use this point here. Okay, I'm going to use -2 and -60. All right, and what's the purpose of figuring out a point is so that we can solve for my a value. So with that being said, I'm going to do y equals to a times x minus 1 times x minus 3 times x plus 4 squared. And I'm going to use -2 and -60 to help me solve for my a value. So this is my x, this is my y, so I'm going to plug it in now. So -60 equals to a, -2 minus 1, -2 minus 3, and then -2 plus 4 squared. Let's simplify everything inside the brackets. -3 times -5 times 2 to the exponent 2. Now all of this here is defined by multiplication. So just make sure that you end up multiplying those numbers together. So with that being said, let's do this. I've got -60 equals to a. So if I do -3 times -5 times 2 squared, which is just 4 for us, I'm going to get 60. All right, and now your job basically is to solve for a. So because I have 60 multiplied by a here, what I'm going to do is I'm going to divide both sides by 60. I'm going to do exactly the same thing here, and that's going to leave me with a equals to -1. So what you found here for me is my a value for this particular polynomial function. And so now you're going to write me the equation for the one that represents this polynomial. So you're going to say, therefore, y equals to negative. We don't write -1 per se. We write the negative, but not the 1. So negative x minus 1, x minus 3, and then x plus 4 squared. All right, so remember, your first step for me here is to create your family of equations. The second step is to choose a point and solve for your a value. And then your third step is to write down the equation for me that I'm looking for. Alrighties, let's take a look at another example. I'm just going to scroll down. So I have this polynomial here, and let's take a look at the zeros that I have. So the zeros that I have are at x equals to -3, and then I have another 0 here at x equals to 1. So at x equals to -3, that's a very straightforward 0. It goes right through. It's to order 1. But if I take a look at x equals to 1, though, I've got a really weird-looking 0 that's occurring there. What's happening? Well, as we discussed in class today, not only can my 0 look like there's a vertex on it, but it can also look like there's a cubic function on it, which is what's happening here right now. In that case, that's going to indicate that we have a 0 that's to order 3. So when we create my equation, right, our generic one, which we still have the a in the front, x plus 3, that's going to correspond to x minus 3 as a 0. X equals to -3. And then at x equals to 1, so my factor, x minus 1, it's not going to be to order 1. It's not going to be to order 2. It's going to be to order 3 here. And the whole reason is because it looks like a cubic function on that 0. So x minus 1 is going to be to order 3. Now that we've gotten our family of polynomial functions created, corresponding to what information that I have right now based on zeros, I'm going to choose a specific point on my graph to then solve for my a value. So my second step, I'm going to do y equals to, a, x plus 3, x minus 1 cubed. Now let's take a look at a point that I'd be interested in using. In our case here, I think it might be worthwhile for us to use the following point. I'm just going to highlight it in green. So that's the point that I'm going to use. That point for us is -1 and 16. All right, -1, oh, not 16, -16. So we're going to use that point to help us solve for my a value now. All right, so our goal is to solve for this a value. So let's plug it in. Remember, this is my x, this is my y. So -16 equals to a times -1 plus 3 times -1. Just going to erase this. Give me 1 second. So -1 minus 1 to the exponent 3. So I've got -16 equals to a times 2 times -2 cubed. -16 equals to a. Now 2 times -2 cubed, that's going to give me -16. Make sure when you do this, you put brackets around -16 because in the past I've had a lot of students write down a minus 16 instead. So I'm going to divide both sides by -16. That's going to give me a equals to 1. So my a value for this polynomial function is just 1 here. So my third step is going to be writing out my equation. So it's going to be y equals to x plus 3, x minus 1 cubed. We don't write the 1 in the front here just because it's assumed that it's a 1 there. So please make sure you do give a try to some of the graphs that I gave you guys in the worksheet. It's a good way to practice so that when you're sketching as well, that you're sketching the correct